Hello, everyone. Today, I'm going to be talking about Envoy Mobile, what it is, and the upcoming networking revolution. Before we get to that, let's take a step back and talk about the apps that we all work on. Typically, I think most of us, when we go to write an iOS app, we set our systems up something like this, where we have the iOS app, and then we have some sort of back-end web service, and they communicate with each other using some sort of networking infrastructure on both sides. On iOS, this might look something like URL session, or maybe a wrapper like Alamo Fire. And on the back end, maybe use something like Flask or any other different networking library. And at most small to medium-sized companies, this is totally fine, and everything works really well just as is. As the company grows, though, and as the team scales, these can actually cause some problems because of inconsistencies inside of the networking layers. And I'll get into what some of those problems are in a moment. But assuming that we have these problems, ideally we should be able to solve them if we're able to ship the same networking library on both the backend and the client. And at Lyft, we actually solved this using something called Envoy. And I'll get into what that is later on in the talk. But before we get to that, let's talk about what data we send, and then we can start to dig in a little bit as to how we send that data. So early APIs at Lyft were developed using a flow something like this, where we would have engineers from iOS, Android, and server kind of collaborate on some sort of tech spec, maybe a Google Doc. And then after they decide on what they want their APIs to look like, they go their separate ways and handwrite some code in Swift, Kotlin, Python, or Go. And it probably looks something like this in Swift. I'm sure many of us have actually written code almost identical to this, where you create a dictionary, and then you send it up to the server using a hand-typed path, for example. And this came to cause a few problems as the team scaled. As Keith mentioned earlier, we now have over 70 iOS engineers, the same number of Android engineers, and then over 1,000 other engineers at the company. And so as we handwrite all of these APIs, inevitably someone is going to have a typo and make some mistakes. And so as a very simple example of this, let's say we have an iOS app that sends one key up to the server, just saying hello. And then the same thing is implemented on Android, except it's not actually the same thing that was implemented on Android because they introduced a typo. Depending on when this problem is found, either we end up hotfixing an app or delaying a release, or the server ends up actually implementing some logic to either check whether one key is there, a different key is there, or maybe even whether an iOS or an Android client sent this data. And this makes it really difficult to kind of figure out how the API actually works without reading through each individual code base. The second problem is that it's very hard to see deserialization failures. So in the early days, Lyft actually open sourced a library called Mapper. And Mapper essentially allowed engineers to convert like JSON dictionaries into typed Swift models. And this is, for example, what an initializer might have looked like. And inside of here, there's a couple of places where things can break. So the first, for example, is optionality. You can see that that try means that in some cases, iOS might actually require that field, and on Android, maybe the field is optional. So the backend engineer decides, I'm not going to send this field, and then Android works fine, but iOS blows up. Secondly, you'll see that you basically end up casting with dictionaries, and you don't really know the type of what you're deserializing, and you're going to try to see if that type is there, but there's no contract that what you got is actually correct. And then thirdly, we're back to typos. I don't know if you've even noticed that. And finally, the biggest problem that we had with this was that there was no single source of truth. So if an engineer wanted to understand how an API actually worked, they would have to go and read the iOS code, the Android code, and the server code, because there was no guarantee that they all actually worked the same way. And to help fight this, some engineers got together a couple years back and decided to implement a system that allowed engineers to define APIs using YAML. And it looked something like this. It was very basic definitions. And this was developed as a passion project, so it wasn't like an infrastructure team that actually ended up supporting this. And the results of this were more or less mixed. So there was manual code generation from these YAML definitions that was available, but it was only available on Android, and those engineers still had to generate it locally and then check in the output into the Android monorepo. Secondly, there was still no integration on iOS or server, so this means that there's basically it didn't change the workflow of iOS or backend engineers, and they still handwrote everything. And this led to the continued inconsistencies that we saw before and the same lack of one source of truth. So when my team, called Client Networking, we came into existence about a year and a half ago, and the recurring problem theme that we saw when we started investigating this was that there was a general lack of consistency across platforms. So there was no contract really in place regarding APIs. And we needed one source of truth that provided guarantees for the behavior of APIs across all platforms. And to do that, we wanted to create one source of truth where every API would live. And from that, we could then generate implementations on all of our different platforms, not just Android or not just iOS. And we did that using two things, IDL and Protobuf. IDL stands for Interface Definition Language, and it's more or less a concept that allows you to define the structure of APIs in a language-agnostic way. So it's not Swift, it's not Kotlin, but it's something that is abstract enough that's very easy to read and can be translated into multiple different languages. And so we took a look at our old workflow, and we envisioned a new workflow that still originated with a tech spec, but instead of engineers then taking that tech spec and then writing some implementation by hand, they would actually go and start collaborating in IDL on some definition. And we created this IDL monorepo where we would check in these API definitions. And then after that, we actually had code generators that would run and output Swift and Kotlin and backend service code. The implementation detail of what IDL looked like was protobuf, or protocol buffers. And you can think of this as essentially a language-agnostic way for defining and serializing APIs. So this is basically the language that we ended up writing these IDLs in. And there's a couple of reasons why we chose protobuf. I'll give you some examples of what it looks like in a minute. But one, it's very simple to write. It looks a lot like Swift structs, basically. Secondly, there are open source code generators available for a lot of different languages, including Swift. Thirdly, it actually supported JSON, and so it would be backwards compatible if we wanted to migrate all of our existing APIs over to use protobuf, which was really big in our case because we wanted to maintain that functionality. And lastly, it actually did support a new optimized wire encoding, which is actually much more compressed than JSON, and so it kind of kept the doors open if we wanted to optimize this further in the future. So I'll give you a brief introduction into what protobuf looks like and kind of how you would end up using it. So this is a very basic protobuf definition. And the first thing that you'll notice in this definition are messages. And messages you can think of more or less as Swift structures. So they're just models that contain different fields. And those fields are, in this case, they're numbered. That's more or less the implementation detail of how protobuf encodes its fields. But just as you would in any other programming language, they have primitive types, and you can also nest your own custom messages inside of there. Thirdly, we have services. And a service you can think of as basically just a collection of APIs. I know some talks earlier have mentioned service modules, and this is a similar concept where you basically collect your different API definitions under that namespace. One of the last things you'll see is an RPC, which stands for Remote Procedure Call, and this is really the crux of the API definition. So you can think of it as a function that basically takes an input, in this case a foo request, and always returns a foo response. And this is a very strict contract between a client and a server that they will always send data structured as a foo request, and they will always get that data back in the foo response. And the last piece, we actually added some custom annotations so that we could define things like the path or the HTTP method or things like that. So going back to our IDL pipeline, engineers would then check in a protobuf definition, which is foo.proto, and that would get fed into our code generators. From there, we actually generate 11 different languages that we support at the company, including Swift and Kotlin. And then on mobile, we actually take that a step further, and we pre-compile them into static libraries on iOS. And this is actually using Bazel, as Keith mentioned in an earlier talk. So what does it look like to actually use protobuf in Swift? If I actually wanted to consume this, how does my workflow as an engineer change from having to handwrite dictionaries? Well, We actually wrote our code generators in-house. I mentioned that they're open source, and we use some open source code generators. But for Swift and Kotlin, we actually wrote our own. And I'll get into that a little bit later. But the main thing that allowed us to do is to customize the implementation of what the APIs actually performed under the hood when engineers consume them. So this probably looks very familiar to you. It's just a couple of structs that conform to codable and equatable. And there's some fields in there just as they were defined in the Protobuf definition. And there's some other things that these conform to that are used later on by different implementations. But as an engineer, this is pretty much all you care about. Second, we generate APIs. And these are actually based on RX Swift. So we expose an interface as a protocol, which basically takes in that request and then returns an RX single that contains the result, which is either a successful response or a typed error. So if you get an error back, you actually can read some of the fields on that error that the server returned. And then in addition to that protocol, we also generate the production implementation as a struct. And so these are based on the name of the service as defined in the Protobuf definition. And one thing to really note about this structure, and this is why we in-housed some of those code generators, is we can actually abstract out the entire implementation of the networking that's performed under the hood. So engineers only really need to care about this public interface that's available in the protocol when they go and write their features. They don't need to worry about the wire format, like whether it's JSON or whether it's Protobuf or how it's encoded. They don't have to worry about any of that. And we, as the networking team, can actually change out how that works at a later time. The last thing that we generate are mocks. So there was some talks earlier about testing and generating mocks. And we actually do generate mocks as well for engineers. And we pre-compile them into separate modules that can be depended on by tests. And these mocks basically implement a default behavior for engineers. And then they're really easy to inject content into so you can test your features. And this is basically what it looks like to use an API. So you pull in that client API using maybe some dependency injection accessor, and then you call that function update food just as you would any other function in Swift. You pass in a request, and then subscribe to the result, and you either get a successful value or a failure back. It's really easy to use. And so the results of this were, first off, we finally had our one source of truth for every API. So engineers can stop discussing basically the implementations of the client and the server and can no longer continue figuring out the implementation details that maybe iOS wrote it this way and Android wrote it this way. There's a guarantee in one place that they can just go to and read a very simple Protobuf definition and understand exactly how the API works across all three platforms. In addition to consistency in the actual data passed around, the interfaces are actually the same. Myself and someone else wrote the code generators for Swift and Kotlin, and the outputted interfaces are almost one-to-one. In fact, you can look at them side by side, and they're more or less the same. The generated code is super easy to use for engineers. It's wrapped in RX. It's also highly testable. And as I mentioned earlier, the wire format is fully abstracted, which takes us to the next thing. Now that we had the wire format abstracted away, and we didn't have engineers having to write JSON mappings or APIs by hand, we started thinking about how we could start optimizing the transport layer to better benefit our users. And so if we look at the existing system we had, where the client basically sent a JSON request to the server would process it, and then also respond with a JSON request, we started thinking about how we could optimize this a bit more so that we could compress that payload and make it smaller. And the way we did that was through something called content negotiation, which basically allows clients and servers to talk to each other and say what content types they support over the wire, rather than just making an assumption that everything will always be JSON or everything will always be Protobuf. And the way this works is the client continues to send its JSON request up, but in addition to what it sent before, it also sends an accept header saying, hey, I know how to read JSON as well as Protobuf. We then installed some very thin middleware across every backend service that we have, which essentially takes that request and looks at it and says, OK, what can the upstream service read? So if the upstream service can actually read Protobuf, it can take that JSON and convert it to Protobuf and then pass it to the server. The server can then get it and respond either in Protobuf or JSON. In this case, let's say it responds with Protobuf. And that same middleware looks at what the client said it knew how to read. And if the client knows how to read Protobuf, it gets a more optimized response than it would have if it only knew how to read JSON. And if not, the middleware can actually convert that Protobuf back to JSON. And we saw some really huge performance improvements with this. These are our 4 biggest endpoints and their response sizes. And you can see that a lot of the payloads were almost halved as a result of switching just the content and the way it's formatted across the wire. So in addition to over 40% reduction in a lot of our APIs, we started getting faster response times because there's less data to send, and our success rates also went up because the data was getting there faster and there was less of it that had to be transmitted. And the really important thing here is that it was completely transparent to engineers. So we were actually able to run this rollout as an A/B test underneath every single API at the company without any product engineer having to change their code because we had abstracted out the networking layer into this very simple interface. So after we rolled this out, we started thinking about what if we wanted to change how we send data rather than what we send. So for example, instead of just changing the content from maybe JSON to Protobuf, what if we could change the actual protocol? So what if we wanted to go from HTTP2 to HTTP3 or QUIC or some other future protocol? And on the back end at Lyft, we actually solved the consistency problem using something called Envoy. And Envoy is a C++ proxy that abstracts networking away from services. So you can think of it kind of similarly to how we abstracted networking out on iOS. And it essentially is a project that was open sourced by Lyft and is actually used by quite a few companies, including Airbnb and Uber, Google. And it's typically deployed on service mesh infrastructures. And what I mean by that is instead of just having one server where all of the code lives, we typically have many different microservices that have different pieces of code on them that communicate with each other. And that allows them to scale independently and fail over independently. And the way Envoy fits into that is we actually run an instance of Envoy on every single instance of every service. And so we essentially have this mesh of different services that communicate with each other. And in each case, Envoy is responsible for basically relaying every request and response that each service sends. And Envoy knows how to speak a lot of different protocols among different things, and it can actually convert requests between different things. So for example, a service that speaks HTTP1 can talk to a service that speaks HTTP2, or gRPC, or other different protocols. And they don't actually have to worry about the implementation details of how a different service knows how to talk, because Envoy does that for them. And the way Envoy implements all of these systems is through the concept of filters. And filters are essentially common functionality that gets executed for every request or response that a given service sends. So you could write a set of code and then deploy it onto Envoy, and that will get called every time a request or response happens. And it's able to read the data that's sent, and it can actually mutate it or keep it from being sent or cancel the request and continue doing other things with that. So to illustrate what this looks like, let's say that we have a service A, and that service has an instance of Envoy running on it with 2 different filters that are configured. The first filter for a given outbound request looks at that request and adds authentication headers. The second filter takes that same request and then maybe encodes it using something like gzip to make it more efficient before it's finally transmitted off of the service. Then another instance of Envoy running on service B actually receives that request, and it's configured with 2 different filters. And the first one maybe goes and does some validation on the authentication. And then the second one can actually unzip that request. And then service B finally gets the content that was sent to it. And this is really powerful because it abstracts out a lot of this logic from every service and avoids having engineers duplicate code or deploy things manually to all these different services. We can actually just ship it into Envoy and then deploy it everywhere in an abstract fashion. The last piece of the service mesh that I want to mention is what we call a front proxy. So in addition to having instances of Envoy running on every service, we also have what's called a front proxy, which sits on the outside of the mesh and is basically responsible for communicating with the outside world. And so it does things like routing, load balancing, and circuit breaking. and handles all of the requests coming from our iOS and Android clients, and then relays those to our backend services. And so as you can see, there's this nice level of consistency across all of our services, where they all communicate with each other using the same networking stack. They all use Envoy. And if we take a step back, we were originally talking about trying to keep that networking library the same on both our mobile clients as well as the backend. And that's where something called Envoy Mobile comes in. Envoy Mobile is a project that my team has been working on for the past several months. We actually open sourced it earlier this year as a demo, and since then, we've been iterating on it quite a bit, and now it's a library that essentially wraps Envoy in Swift and Kotlin and can be treated just as any other networking library, and you could actually swap it out for something like URL session. And the mission of the library is to start to bring the functionality that we have on our backend and to bring the consistency that it has onto mobile. And with Envoy Mobile, we basically bring mobile into the service mesh, and it just becomes another node there. And we now have this consistency across our entire stack. And this unlocks a lot of really exciting things. First, we now have one networking stack across all of our platforms, so we can now be confident that everything works the exact same way across iOS and Android and our backend services. This also means that we can write functionality once and ship it everywhere. So for example, we could write authentication logic into a filter and then ship that onto our mobile clients as well as our backend services, and then no one on iOS, Android, or the backend service has to worry about how auth is implemented. And if we need to change it, we just change it in one place. Thirdly, we're actually able to start experimenting with and testing new protocols. So some of you may have heard of Quick or HTTP3. But it's an upcoming protocol that at some point Apple and Google will end up supporting on iOS and Android, but we're actually able to start testing it much, much faster than that because we use the same networking stack across all of our platforms. So we can actually write that functionality into Envoy and ship it everywhere and start testing it really quickly. And lastly, we're actually able to get consistent stats and monitoring across all of our platforms. And we've actually started testing this in the Lyft Rider app, and these are some real-time stats that we've started seeing. So you can actually see these are real requests coming from Lyft employees, and they've begun testing it, and we can actually see these stats, which is really exciting. So by transparently integrating Envoy Mobile, we are able to start experimenting with new protocols like HTTP3 and changing how we send data and not just what we send. And it's a new way to think about consistency across all of our platforms. So we really think Envoy Mobile is going to help revolutionize how we enable network consistency across all platforms. And it's open source, so if this is something that interests you, I would strongly recommend checking it out on GitHub, or I'm happy to chat afterwards. Thank you.
Thank you very much, Michael. Anyone would like to ask a question? Here we have one.
Hi. Definitely, Envoy looks great. Now I'm curious about the model layer. Not sure how Envoy handle this part. I say that we are covering networking layer, but we have this multi-platform support. But not sure in what moment is Envoy takes care of network layer, or are the developers responsible of this part?
For the model layer, you said?
Yes, because if the user are fetching the information, like I'm just imagining in the old way, fetching the data.
Oh, yeah.
How we can decode this data? Is Envoy in charge of this part too, or are the developers responsible for this?
So the way that we treat the system is Envoy is basically responsible for relaying the information. So it's just like a networking stack. You can think of it as a one-to-one replacement for URL session. That would be like the level that it operates at. On top of that, the infrastructure that we've written on top of Envoy, which we're also planning on open sourcing sometime next year, like the code generators, for example. The code generators are something that output conformance to different serializers and deserializers for models. And then basically the networking layer, we have this little layer of like glue code that basically takes those interfaces and binds them to Envoy interfaces. So when we open source the code generators, we plan to open source those bindings as well. So ideally, you'll be able to just write a protobuf definition, look at the output, and then just consume the output, and it'll be routed through Envoy.
Thank you very much. Anyone else? There it is, one candidate.
Up here. So I'm curious about how GraphQL fit in this research for you. I know it may be a different layer. It doesn't necessarily involve with networking.
Yeah.
But how did it fit? How did you go around GraphQL?
So we talked a little bit about GraphQL. It's kind of, that's more in line with the protobuf discussion, I guess. At Lyft, we don't really tend to need a whole lot of dynamic querying. So like Facebook, for example, GraphQL makes a lot of sense because of how their data is structured. Like you're browsing people's feeds, you're going down through really deep into this tree of different data. At Lyft, you're mostly consuming like information like the current ride or your current trip or different information like that. And it doesn't really need a ton of like client-side querying logic. So we don't currently support GraphQL with our like model code generation layer, but it's something we've talked about. But right now we don't use it.
Okay, we have time. There we are. For one more.
Hi, I'm Luis. Adding extra layers of abstraction to the networking on mobile and server, doesn't it incur in a performance backlash from the server side or the mobile side? How you benchmark that?
Yeah, so we have not seen any performance backlash. Envoy itself is written in C++, and there were basically two reasons for that. The first reason was performance. So it's very, very parallelized, and so it operates extremely fast. The second reason for that was it was originally written that way to be more extensible, so it could be shipped onto different services in different languages, and that also allows us to bridge it up to native clients. But we have not seen any performance problems just because so much work has been put into making it operate very quickly. Yeah.
Okay, thank you very much,
Thank
Michael.
you.